Welcome, everyone. I'm going to just set the stage here and talk about quantum computers, what they are, and importantly, what they are not. Oh, hello. And let's see if this works. So I'm hoping that by the end of this talk, you will essentially have a pretty good idea of what a quantum computer is, and hopefully an idea that aligns somewhat with what the research community thinks that a quantum computer is. Because quantum computers is something you hear a lot about in the popular press, and the impression that you might get away with from reading a couple of headlines might diverge significantly from what scientists actually believe that these things can do. So that's sort of what I want to talk about. I want to talk about why I'm excited about quantum computers personally. And I want to show that those are not necessarily the same reasons why a lot of non-specialists out there seem to be excited or hyped up about them. So this is a headline I took from just last week. I think it's like 7 days old. Has the potential to change almost everything. Scientists to channel quantum power. I literally just Googled quantum has the potential to, and just grabbed the first one I found. Like there's a million of these out there. Sure, that would be great, right? If it could change almost everything. Here's another headline from also 7-8 days ago. Google launches a $5 million prize to find actual uses for quantum computers. Like there seems to be a mismatch here, right? It's not just me. Now, Google, of course, are actually building these devices, so you would think that they have a vested interest in using them for stuff, evidently. And based from these two sources, I would rather trust the Google engineers to know what they're doing, since they are quite literally among the world leaders when it comes to building quantum devices. But what is up with this mismatch, right? Why are people saying that these have the potential to change almost everything, and then at the same time you can't find a single use case for them? Like, what is happening here? Here's another one from a Norwegian newspaper. This one reads that machines like this one can kill the internet. All right, okay, is this true? Like, I've just told you that this is probably overhyped BS, right? Is this also overhyped BS then? Like, what is going on? So this is sort of like, by the end of this talk, I hope you feel that you have the answers to all of these questions. So I've just, from the top of my head, just sort of pulled out a lot of like sentences that you might see in headlines in popular science press. So stuff that I feel like I see all the time in the popular science is, for instance, we are reaching a physical limit to Moore's law, this idea that computer chips can get more and more powerful. So that now we need to transition to quantum computers in order to be able to continue the trend, because the physical limit is about atoms, right? So why not make computations on the atoms, then you can continue the Moore's law trend. All right, sounds plausible. Here's another one. Quantum computers can instantly solve hard problems by trying all solutions in parallel. Very common understanding of how quantum computers work. Not entirely accurate, let's put it like that. Quantum computers will accelerate the green energy transition. This one I've heard a lot, and honestly, it confuses me. I'll talk more about it in a minute. Quantum computers will revolutionize artificial intelligence. Well, will it? And quantum computers, finally, can break any code. Not entirely. So all of these statements are either, straight up false or completely unjustified. But there is a silver lining. Each of them are based on a grain of truth, just like inflated out of proportion, or rather based on a misunderstanding of that underlying truth. So that's what I want to talk to you about. I want to talk about what these grains of truth are that lead to these very common misconceptions about quantum computers, so that you can still be excited about this new technology that's on the horizon, but have realistic expectations of them. All right, so let's start off with the basics. Like, what is actually a quantum computer? What are we talking about here? So here I drew one of these chandelier kind of constructions that you typically see. Now, the entire chandelier thing is actually just a big fridge. So for each level that you go down here, they, I don't know, half the temperature or something like this until they reach almost like absolute zero. So that's like minus 273 degrees Celsius, I believe. And at the very bottom here, there's a very, very special chip that contains just tiny, tiny bits of information processing. But in order to function, they need to be very close to absolute zero. So this is why you have this big chandelier that cools down the entire system, and then you get something working down here. So a normal bit is typically, not typically, it is always either 0 or 1. And that is the baseline of all computation, right? So computers, they make calculations with numbers that range from 0 to 1 and nothing in between. And then you just have a bunch of them, like as many as you need to make your calculation. So a byte, for instance, is 8 bits. And then if you have a gigabyte, that would make it, I guess, 8 billion bits. And that's how they work. So this is the fundamental unit of information processing that we are replacing with quantum computers. So the very fundamental bit is now becoming a qubit. And I've drawn it as a sort of circle here because the qubit can be in any number of so-called states in between 0 and 1. And if any of you have ever read or seen a popular science thingy about quantum mechanics, you may have heard about Schrödinger's cat, which can be both dead and alive at the same time. As long as you're not looking or looking at the cat or opening the box, it can be in this superposition state of both dead and alive. But the moment you look at it, it sort of decides, right, whether it's dead or alive. That's the same effect that we're talking about here. So if dead cat is 0 and alive cat is 1, then you get exactly a qubit of information in the Schrödinger's cat experiment. Another thing that you get, which is very important, is something called entanglement. And this is where you have very strange, very difficult to explain correlations between the qubits. And this correlation is, it does not seem to respect distance, which is very strange. Like you can have a qubit here, and then you can send a qubit to a different solar system. And the moment you look at your qubit here, it's as if the other qubit notices immediately that it has been looked at as well. And this is what made Einstein call it spooky action at a distance, because it doesn't seem to respect this speed of light limit that his theory of relativity normally imposes on communication and travel and everything. Now, you might think that, okay, so I can make an instant telephone to a different solar system using this. Turns out no, but for very difficult to understand and complicated reasons that even Einstein didn't get to wrap his head around. Let's put it like this. But let's look at the bright side. We have this thing. Can we use it? Turns out the answer is yes. Entanglement in the quantum computing framework is a resource that we can use to build algorithms that cannot be processed on a normal computer. So these are the two main ingredients that make quantum computers different from classical computers. It's superposition and entanglement. And if you want to know more about them, read a book on quantum physics. There are a lot of good ones out there. All right, so let's go through these questions then that I posed in the beginning. I should ask, by the way, is there any questions right now about this? Anything you would like clarified? I know it's kind of confusing, but it's not crucial to the story that you understand this, but I love talking about it, so. All right. I'll be moving on then. So the first statement is that now that Moore's law is reaching its physical limit, we need quantum computers to continue the trend. So Moore's law is this idea that computing power, as measured in the number of transistors on or rather the density of transistors on computer chips, should double roughly every 2 years. And it's an empirical law that an engineer came up with way back when, just observing how development had been going. And it seems to explain actually rather well the explosion of computing technology that we've had over the past 60, 70 years. And But it is reaching a limit, a very hard physical limit, because you can make your transistors smaller and smaller and smaller, but at some point they are literally only made up of a couple of atoms. And at that point, you can't really go any smaller. You can't make smaller atoms. And the other thing is that at that point, a lot of quantum effects actually start to mess with your transistors. So it turns up in sort of noise, in imperfections in the construction. So the idea then is that, oh, okay, we have a bunch of annoying quantum effects here, but what if we use them instead, right? And then you can just continue this trend. Well, yeah, but then the impression you get just reading this statement is that, all right, in 50 years from now, I'll have a phone like this, and it will be a quantum computer that will fit in my pocket, and it will have a billion times or a gazillion times the computing power of the best supercomputer in the world today. And that's just not the case, right? So the grain of truth here is that quantum computers do not face the same physical limits, sure, but they are not just better computers, right? They are different computers. They're a completely different paradigm, and they are never going to replace your pocket phone, among other things, because it seems that we need them to operate at absolute zero temperature in order for them to function. So you should think of them as specialized computers, specialized chips that can do certain things very well when combined with normal classical computing power. As an analogy, you can think of it as, a graphics card, right? You have a CPU, a computing processing unit, but you also want a graphics card because it turns out that you can make a different kind of chip that does graphics way better than a CPU. So then the CPU is offloading that work onto the GPU, and then the GPU sends the results back to the CPU, and everything, it's a collaboration. So maybe you could think of it like this then, at some point, maybe in some server farm over in the US somewhere, there will be a QPU, a quantum processing unit, that your phone can contact via server access and sort of offload some very specific tasks to it, and then you get the results back. And it will be like a slight increase in efficiency or something like this. But this is the important part. It's not just a super duper computer. It's something different, something else. All right, that was the first question. Question number 2. Quantum computers can instantly solve hard problems simply by trying all solutions in parallel. Yeah. If that were the case, the future would be nigh. Like that would be completely amazing. It would be completely revolutionary. Like the first thing that would happen is that you would get $1 million from the Mathematical Clay Institute, probably, for having proven that P equals NP. And then everything else sort of just becomes this amazing Futurama sort of society where everything runs smoothly and everything is optimized. That's not going to happen. Like, this is literally not how quantum computers work. But again, there is a grain of truth underlying it, because there is a quantum algorithm that functions more or less exactly like this statement, and it's called Grover's algorithm. And it really does run all possible solutions in parallel and then output not the solution, but a state that when you observe it has a tiny fraction of a higher likelihood that you will hit the solution you want. So the problem here is that you need to run this Grover's algorithm in series, like millions and millions of times, until you've more or less wasted as much time as you were going to gain to begin with. So the problem is the word instant. It's not exactly instant. The speed up, the efficiency gain you get from this algorithm is very, very slight. And in all likelihood, it will be far, far, far into the future before any quantum computer can use Grover's algorithm to compete with classical optimizations. So whenever you hear about people saying that optimization, logistics, even finance, stuff like this will have huge gains from quantum computers, more likely than not, this is the algorithm that they are referring to. And theoretically, there is a measurable speed up there, but it is so small that it will likely not manifest within maybe the next 50 or 100 years. So don't hold your breath whenever you see stuff like this. Quantum computers will revolutionize optimization. No, it won't. All right, so this is sort of related. Quantum computers will accelerate the green energy transition. Right? Like if this were the case, then sure, you could optimize everything, and then you would have your green energy transition Futurama instantly. Perfect. But once again, this is not what is going to happen. So the grain of truth here is that quantum computers are very good at one very specific thing, namely simulating quantum physics. It is almost circular, right? Like, of course, something quantum would be good at doing something quantum. It feels like a self-evident statement. But it turns out that quantum physics is actually a huge problem to simulate on classical computers. It is very difficult to do so. And we believe it is not possible to find an efficient algorithm to simulate quantum physics on normal computers. If it were possible, we wouldn't need the quantum computers to begin with. So this is how quantum computers were thought up to begin with. They were always envisioned to be just very fancy physics simulators, right? And they are very good at it. So quantum simulation could open paths to new technologies that could, if that were to happen, help accelerate the green energy transition. So example, there is a particular case about greener fertilizers, because producing fertilizers, as far as I understand it, is a very energy costly thing at the moment. But we know it should be possible to do it more efficiently because it happens in nature. So maybe the key to understanding how it happens in nature is due to some quantum effects that we haven't understood yet, right? It could be this now blooming field of quantum biology gets involved here, for instance. Maybe that would help, sure. Better batteries definitely would be a huge help. If you want to decarbonize airplanes without, I don't know, going back to using hydrogen zeppelins or something, then you really need very much higher energy density in your batteries than what we have today, right? And there are a bunch of, promising battery technologies that people are researching nowadays. But at some point, I expect that stuff like quantum chemistry and just quantum material design will become necessary in order to build, for instance, better batteries. And then maybe having good quantum simulators will help you, in which case it could help accelerate the green energy transition. Third thing, and I note that this is the holy grail here, is of course room temperature superconductors. This is something that people keep saying, yeah, it's only 5 years off, right? It's one of those magic technologies. And if you really got good room temperature superconductors, then this society would be very close. Like it would be an incredible technology that would unlock all sorts of capabilities for humankind. And it is fundamentally a quantum effect. You need quantum physics to explain superconductivity. But the only way we know how to make superconductors nowadays is, once again, if you cool them down to absolute zero, then you get superconducting effects. Alternatively, you can raise the temperature a little bit, but then you need pressures that are like on the magnitude of the core of the sun or something like this. And yeah, you don't want to run around with that in your pocket. So if you could get low pressure, high temperature superconductors, that would enable an amazing future. But we don't have that yet. So you should notice now that all of these are speculations on my part, right? I'm really trying to give them the benefit of the doubt, these guys who say this, and I'm trying to imagine, okay, what could they be thinking about, right? Well, it must be this, because the optimization thing is not going to fly. So quantum simulations, sure, why not? Let's hope. Let's see once we actually get these computers. Let's see what people can do with them. All right, this is a fun one. Quantum computers will revolutionize artificial intelligence. So this is, of course, ChatGPT's interpretation of a quantum mind. I thought that was fitting to use AI here. All right, so there is a grain of truth to this, in the sense that there has been a lot of really promising quantum machine learning algorithms up throughout the years. There is a very specific sort of underlying linear algebra algorithm that all of them are based on. And it's like, once you see this linear algebra algorithm, you're like, yeah, it really should be possible to do something with this. And machine learning is sort of the obvious application. So it really does seem like there should be really good quantum machine learning algorithms out there that will outperform any classical algorithms. And people have come up with, good quantum machine learning algorithms. The problem is that every time they have done so, somebody else has come along and said, oh yeah, but we can find a classical algorithm that does exactly the same thing. Now, it is, of course, sort of a win-win situation, right? Because this classical algorithm didn't exist until people tried competing with a quantum world. But so far, all attempts from the quantum machine learning community to come up with sort of the silver bullet or whatever you want to call it, somebody else has come along shortly after and said, oh, hey, here's how to make it classical. Here's how to make it run on a normal computer. And that's sort of the problem with a lot of these statements, is that sure, you can come up with a good quantum algorithm, but it needs to be more than just a good quantum algorithm. It needs to be better than any classical algorithm that you can cook up. And this hasn't happened yet. So this all started out when Ewin Tang, who was a 19-year-old bachelor student at the time, posted 2 papers on Archive that completely broke like both of the leading candidates for quantum machine learning algorithms. And this meme was posted on Twitter the day after. It was hilarious. I remember it very well. I'm still impressed. She was 19 when she did it. Like, how? I don't know. There is also a silver lining with quantum machine learning. So recently, I think it was a year or 2 ago, a couple of researchers were able to prove that if you have quantum input data, then you can use machine learning algorithms to get something that is actually better than a classical computer can probably ever do. But how do you get quantum input data? And when are you interested in quantum input data? These are at this point essentially open research questions. Very, very interesting open research questions, mind you, but it's not something that industry is going to be ready to jump on in a year or 2, right? But it's very cool. So let's see where it goes. I'm not saying that this is never going to happen. Like, it could be that tomorrow a new algorithm drops and nobody is able to make a classical version of it. I'm just saying it hasn't happened yet. So when people say it will definitely revolutionize AI, it's just an unsubstantiated claim. Thank you. All right. And finally, we get to sort of the topic of the day, right? Quantum computers can break any code. Here's Andrew Yang, former presidential candidate, I believe, in the United States, saying that Google achieving quantum computing is a huge deal. It means, among many other things, that no code is uncrackable. Great. So we should all just go home then, right? Like, what are we doing here? This is simply false. Like, there are codes that have been known since literally the 30s that you can prove can literally never be broken. Like, this is no secret. A quick Wikipedia search would tell you this, but that was too much for Andrew Yang, apparently. But of course, this one also is based on a misunderstanding of a pretty big grain of truth. And that is that quantum computers can break all the popular choices of asymmetric cryptography that have been in use since the 1980s. And that's pretty big, because the modern internet infrastructure is really built on asymmetric cryptography. Digital signatures enable stuff like bank ID and online banking in general and stuff like this. And so asymmetric cryptography, I should mention, this digital signatures, public keys, and it is as opposed to symmetric cryptography, where you have to exchange keys ahead of time through some secure channel, for instance, by literally just meeting each other and exchanging post-it notes. And if you're, if you're a bank with millions of users, it's very annoying to have to meet every single one of those millions of users to exchange post-it notes. So modern digital infrastructure is literally built on this. So when people are talking about a quantum apocalypse, this is what they mean, that all the asymmetric cryptography will suddenly be broken. And if we did nothing about it, then that would be a very real, very damaging scenario, and it would be incredibly costly. And of course, nation states are panicking about this too, because there exists state secrets that are secured with asymmetric cryptography. I don't know this for a fact, but I assume. Yeah, and of course, finally, that other crypto that probably some people here care about. Yes, that does include Bitcoin, Ethereum, etc., other cryptocurrencies. So how does it do it? Well, it's all thanks to this guy, nerdy dude. He discovered this algorithm in 1994 that we now call Shor's algorithm. This is then Peter Shor you have on the left here. And it seemed to have kickstarted a race, right? The quantum computer as a quantum simulator was thought up in 1982 by Richard Feynman. And then not much happened. Like, not even, like the research community working on it was literally a handful of people. Like, you could probably count them on one hand, the people who were working on quantum computing. And all of that changed very rapidly in 1994. And all of a sudden, you have this surge of funding from huge nation states like China and the UK and India and the US, I believe, are the four largest ones, with Russia not far beneath. And suddenly everyone is talking about how quantum computers are going to revolutionize everything. And they push a lot of funding into it. And to me, that feels off, right? It feels a little bit dishonest. Like, we knew since 1982 that these are going to be amazing at simulating quantum physics, I mean, and therefore enable new technology development, etc., etc. But it took until an algorithm that could potentially lead you to decrypt state nation secrets before the nations themselves got interested in all of these very egalitarian applications of quantum computers. Like, to a degree, I would almost wish they could just say out loud that, yeah, we want to be the first one to build this so we can crack everybody else's codes. Because it's so obvious, right? But hey, we get the funding, so who are we to complain, right? All right, so how does this Shor's algorithm actually work? So fundamentally, what it does is a very, very simple mathematical operation. It takes some large number n, which the security of your asymmetric crypto is sort of basing on, and then it factorizes it. So if you take these two prime factors I've written here and you do the reverse operation again, p times q, you should get n back. Now, it turns out that normal computers, for big enough numbers, normal computers can't do this. But for quantum computers, randomly, weirdly, unexpectedly, it seems to be easy. And so this operation alone is enough to break RSA, which was sort of the standard back in the 90s, etc. And also modern standards. Diffie-Hellman has been there all along. And then you have, for instance, like elliptic curve digital signature algorithm, which a lot of cryptocurrency and stuff is based on, I believe. And it can do this operation, and then it can do a couple of other operations that happen to align perfectly with exactly the operations you need for asymmetric security. It's strange almost that the only really good quantum algorithm we have found for something other than quantum simulation aligns perfectly with exactly what you need to break asymmetric cryptography. Tough luck, I guess. So yeah, here's a quantum computer churning along happily, merrily, and factorizing 15 to 3 times 5, etc. Yeah, and others that I haven't listed here as well. So essentially, everything was gone in one fell swoop. A lot of people panicked. So when is the quantum apocalypse scheduled to happen, right? Well, in order to break, okay, so we are here. This is a bit outdated graph. So we're in 2024 now, and the biggest quantum computers today has just over 1,000 qubits. So actually, we're on track for this red line here. We don't know if it will continue, but we can extrapolate. Now, research state of the art says that you need 10 million qubits in order to threaten modern cryptography. So let's just draw some lines. All right, you go over there and down there. 2040s maybe, like 20 years from now, something like this. Sounds reasonable, if optimistic. If people say it will be broken by 2030, you can safely ignore them. 2040s, maybe. Or if you continue this trend in the pessimistic line, you get something like 2060s. So if you say between 20 and 40 years until the apocalypse hits, that's not off. But I expect in the next talks we will hear that even still we need to care about quantum safety right now for different reasons. So I will just summarize what I've been saying so far. As far as we know, quantum computers will be good for exactly two things. The first one is simulating quantum nature, obviously. But this is very useful, and this is something to be excited about. The second one is breaking asymmetric crypto. And then essentially nothing else, right? There are people out there looking for new algorithms because we expect, of course, that there should be undiscovered algorithms, but they have turned out to be very, very difficult to find. So solution then, should we just go back to good old symmetric crypto and start, exchanging POSIT notes again? Luckily not. We can do better. We have quantum safe alternatives that have been in development for many years, and they are just now starting to be standardized. And this is what the other talks will be talking about, and this is what is known as post-quantum cryptography. So with that, I will leave it to questions, and thank you very much.
So we will have time for questions if you have one question, otherwise we move to the next talk.
I have one, yeah. So within quantum computing, what are the kind of cool breakthroughs that are also realistic in the near short term?
Usually, what people talk about is quantum chemistry. So simulating large molecules that are still small enough that you need quantum effects to see how they behave dynamically. And if you can simulate these well enough, then you can sort of get all of the chemistry results that have been observed from first principles, which has been impossible until now. So there is actually a sort of an arms race ongoing where I think last autumn, half a year ago, IBM claimed that they had the first result of a molecule that was being simulated on a quantum computer that was not possible to simulate on a classical computer. But of course, 1 month later, a different research team comes and says, hey, we just simulated your molecule on a classical computer. So what gives? Right? But this is a good thing. This is this arms race that's going on there. But this is what we expect will be the first sort of application.
Okay, so anyone more questions to Hans? We have time during the event. So thanks again, Hans. And